Angle between lines in Cartesian form. Welcome, everyone. Today, we are going to explore a fundamental concept in three-dimensional geometry, finding the angle between two lines when they are presented in their Cartesian form. Now, when we move from 2D to 3D space, lines aren't just simple slopes on a flat plane. They are represented by more complex Cartesian equations. When we want to determine the angle at which two of these lines intersect, a key insight is that we don't actually need to worry about where the lines are located in space or which specific points they pass through. Instead, our primary focus will be on their directions. In this tutorial, I will guide you through the process of looking at these Cartesian equations, extracting the essential direction information, and then applying a specific mathematical formula to calculate the precise angle between the two lines. Let's get started. Understanding the Cartesian form. To define a line in three-dimensional space, we need two pieces of information: a specific starting point and the direction in which the line travels. If we have a line passing through a point with coordinates x sub 1, y sub 1, and z sub 1, and we know its direction ratios are a, b, and c, we can write it as a series of equal ratios. Specifically, the fraction with x minus x sub 1 over a equals the fraction with y minus y sub 1 over b, which in turn equals the fraction with z minus z sub 1 over c. In practice, when we are working on problems involving the angle between two lines, we will usually be presented with two separate equations, which we'll call line L sub 1 and line L sub 2. For line L sub 1, we'll have its own set of coordinates and direction ratios, which we'll label with a subscript 1. So, x minus x sub 1 over sub 1 equals y minus y sub 1 over b sub 1 equals z minus z sub 1 over c sub 1. Similarly, for line L sub 2, we use a subscript 2 for all the components. X minus x sub 2 over a sub 2 equals y minus y sub 2 over b sub 2 equals z minus z sub 2 over c sub 2. Now that we've introduced the topic, let's take a closer look at what this Cartesian form actually looks like. Keep these structures in mind, because in the next slide, I'm going to show you exactly which part of these equations is the most important for our calculation. Identifying direction ratios. Now that we have seen the general structure of the Cartesian equations for two lines on the previous slide, let's focus on the most critical step in this entire process: identifying the direction ratios, often abbreviated as DRS. If you look closely at the equations we just discussed, you'll notice that the denominators of those ratios represent the direction ratios of the line. This is where the real information about the line's path is hidden. Specifically, for our first line L1, the direction ratios are a sub 1, b, sub 1, and c sub 1. Similarly, for our second line L2, the direction ratios are a sub 2, b, sub 2, and c sub 2. It is important to understand that these ratios are what describe the slope or the specific orientation of the line within three-dimensional space. Once we have successfully extracted these values, we will be ready to plug them into our main mathematical formula, which we will cover in the next slide. The mathematical formula. Now that we have identified how to extract those direction ratios from the denominators, let's look at the mathematical formula we use to actually calculate the angle. First, it is important to remember a convention in geometry. When we talk about the angle theta between two lines, we are specifically looking for the acute angle, that is, the angle that is less than 90 degrees. To ensure our result is always acute, we apply an absolute value to the entire fraction. This prevents us from getting a negative cosine value, which would mistakenly give us an obtuse angle. Here is the formula. Cosine theta equals the absolute value of the quantity a sub 1, a sub 2, plus b sub 1, b sub 2, plus c sub 1, c sub 2, all divided by the quantity, the square root of a sub 1 squared plus b sub 1 squared plus c sub 1 squared, multiplied by the square root of a sub 2 squared plus b sub 2 squared plus c sub 2 squared. To make this less intimidating, let's break the formula down into two parts. Looking at the numerator, we have the sum of the products of the corresponding direction ratios. You are simply multiplying the x components together, the y components together, and the z components together, then adding those three results. As for the denominator, we are looking at the product of the magnitudes of the two direction vectors. Essentially, you calculate the length of the first direction vector and multiply it by the length of the second direction vector. In the next slide, I will walk you through a clear, step-by-step process so you can apply this formula systematically to any problem. Step-by-step calculation process. Now that we have seen the formula itself, let's break it down into a clear, systematic process. If you follow these 6 steps, you'll be able to solve any problem of this type without getting lost in the algebra. First, step 1. Your very first task is to extract the direction ratios. Look closely at the denominators of your two Cartesian equations. From the first line, pull out a sub 1, b, sub 1, and c, sub 1. Then, do the exact same for the second line to get a sub 2, b, sub 2, and c, sub 2. Step 2, once you have those ratios, calculate the numerator of our formula. We'll call this. To find s, multiply the corresponding ratios together and add them up. That is, a sub 1 times a sub 2 plus b, sub 1 times b sub 2 plus c, sub 1 times c sub 2. Step 3, next, we need to find the magnitude of the first direction vector, which we'll call m sub 1. To do this, take the square root of the sum of the squares of your first set of ratios. The square root of a sub 1 squared plus b, sub 1 squared plus c, sub 1 squared. Step 4, we do the same for the second line. Calculate m sub 2 by taking the square root of a sub 2 squared plus b, sub 2 squared plus c, sub 2 squared. Step 5, now, it's time to bring everything together. Substitute your calculated values into the main formula. You'll take the absolute value of s divided by the product of m sub 1 and m sub 2. This will give you the value for the cosine of theta. Finally, step 6. To find the actual angle theta, you simply take the inverse cosine of that result. In the next slide, we are going to walk through a concrete example using these exact steps so you can see this process in action. Illustrative example. Now that we have understood the theory and the formula, let's put everything into practice with an illustrative example. Imagine a real-world scenario. Suppose you are an engineer working on a building project. You have two structural beams meeting at a joint, and to ensure the stability of the entire structure, you need to precisely calculate the angle at which they intersect. In our mathematical model, these two beams are represented by two lines in Cartesian form. The first line, L1, is given by the equation x minus 2 all over 1 equals y plus 1 all over 1, which equals z minus 5 all over 0. The second line, L2, is represented as x minus 1 all over 0 equals y minus 2 all over 1, which equals z minus 3 all over 1. Let's walk through the solution step by step, just as we practiced in the previous slides. First, we need to identify the direction ratios. Remember, as we discussed earlier, we only care about the denominators. For line L1, our direction ratios are a 1 equals 1, b, 1 equals 1, and c1 equals 0. For line L2, we have a 2 equals 0, b2 equals 1, and c2 equals 1. Next, we calculate the numerator of our formula, which we'll call s. This is the sum of the products of the corresponding ratios. So, we multiply 1 times 0, plus 1 times 1, plus 0 times 1. This simplifies to 0 plus 1 plus 0, giving us a total of 1. Now, we need the magnitudes of these direction vectors, which we'll call m1 and m2. For the first line, the magnitude is the square root of 1 squared plus 0 squared, which simplifies to the square root of 2. For the second line, the magnitude is the square root of 0 squared plus 1 squared, which also results in the square root of 2. Now, we apply the formula we learned. We take the absolute value of our numerator, 1, divided by the product of our two magnitudes, which is the square root of 2 times the square root of 2. Since the square root of 2 times itself is simply 2, our equation becomes the absolute value of 1 over 2, which equals 0.5. Finally, to find the actual angle theta, we take the inverse cosine of 0.5. This gives us an angle of 60 degrees, or, if you are working in radians, pi over 3. As we move to the next slide, keep in mind that while this calculation was straightforward, there are a few common pitfalls you should watch out for to ensure your results are always accurate. Common mistakes to avoid. Now, before we wrap up with our final summary, I want to pause and discuss some common pitfalls. Even if you understand the formula we just used in our example, it is very easy to make a small error that leads to a completely wrong answer. First, watch out for using coordinates instead of ratios. When you look at the Cartesian equations we studied in slide 2, you'll see both points like x sub 1, y sub 1, z sub 1, and the direction ratios a b and c. A very common mistake is to accidentally plug those starting points into the formula. Please remember, the angle depends entirely on the denominators, the direction ratios, not on the specific points the lines pass through. Second, do not forget the absolute value bars around the numerator and denominator. If you ignore the absolute value, you might end up with a negative value for cosine theta. While mathematically possible, a negative cosine would give you an obtuse angle. In our geometry curriculum, when we ask for the angle between two lines, we are conventionally looking for the acute angle, so that absolute value is your safeguard to ensure your answer is correct. Finally, always check the form of your equation before you start extracting your ratios. The formula only works if the numerators are in the form of x minus x sub 1. If you encounter an equation where the numerator looks like 2x minus 4, you cannot simply take the 2 as your direction ratio. You must first divide everything by 2 to simplify it to x minus 2 over 1. If you don't simplify it to that standard form first, you'll identify the direction ratio as 2 instead of 1, and your entire calculation will be off. Keep these 3 points in mind, and you'll avoid the most frequent errors students encounter. Key takeaways. First, always remember that, when you are looking at the Cartesian form of a line, the direction ratios are simply the denominators in those ratios. As we discussed in slide 3, these are the numbers that tell us how the line is oriented in space. Second, it is crucial to understand that finding the angle between two lines is essentially the same as finding the angle between their direction vectors. We aren't worried about where the lines are located in the coordinate system, but rather the direction they are pointing. Third, to calculate that specific angle, we use the formula where cosine theta equals the absolute value of a sub 1, a sub 2, plus b sub 1, b sub 2, plus c sub 1, c sub 2, all over the square root of a sub 1 squared plus b sub 1 squared plus c sub 1 squared, multiplied by the square root of a sub 2 squared plus b sub 2 squared plus c sub 2 squared. As we saw in our calculation steps, using the absolute value is what ensures we are finding the acute angle. Now, there are 2 very important special cases to keep in mind for your exams. First, if you perform your calculation and find that cosine theta equals 0, this tells you that the lines are perpendicular or at a 90-degree angle to each other. Finally, if you notice that the ratio of a sub 1 over a sub 2 equals the ratio of b sub 1 over b sub 2, which also equals the ratio of c sub 1 over c sub 2, then the lines are parallel, meaning the angle theta is 0 degrees. All right, we have reached the end of our tutorial. Let's wrap everything up by reviewing the key takeaways from today's lesson to ensure you have a solid grasp of the concept. I hope this summary helps solidify your understanding. Keep practicing these steps, and you'll master 3D geometry in no time.